Hi, I would like to present you my talk about scalable, efficient processing and analysis of huge, large audio data sets that we have right now. At least not maybe in recording studios, but around the world in or in specific terms when you create machine learning models. So I'm Pawel Cyrta. Let's just get to know each other. I'm an applied research scientist working kind of freelance way for some agencies, startups, and companies in Spute and audio technology. Previously, I worked in Samsung, R&D, Earcom, Rev.ai, Bubble Ops, to some Tuplix for now these media companies. Um, um, I was a lecturer in Chopin music for also University of Music for interactive sound and design. Right now, lecturing most technical studies about deep learning. And yeah, I'm also kind of artist in a way. I want to present and create my own instruments and learn others how to control and do installations. I was a technical curator for some of them. I to create a workshops since 2009, modeling of sound and media lab. I'm also a composer in interactive scene. Here is the generative composition that I've presented throughout the 6 weeks next to the river in Warsaw. It was interactive, so you can put your hands inside, and there are different shapes and objects like sands, like elements that are microphones, and also there are some sensors that know what the positions, and you can indirectly create the sound and also move around, so you control them. It was a more than 80 channel composition. But anyhow, that's on the side of more artistic side. Here, I am quite into the technology. I was creating a speech recognition for European languages for Samsung for 7 years that were seen in, especially in S7. Also speech to text to speech, also synthesis part right now. So if you want to create such solutions and also for some kind of audio recognition, like audio event detection or scene where you are, you need to have a lot of data. So you need to go through the high performance computer for large set of nodes, and that's my work. So that's my world inside of the audio world, machine learning in audio. But I want to just present you some challenges and that comes with huge audio sets that I typically work with, and show you some solutions. This is not one of many, but let me just start and talk about details later on. Let me just get you throughout the different dangerous waters of machine learning and in terms of audio and the data inside. And the best thing is that there is this array about other techniques that you can cope with a lot of data, and we have plenty of data, and a lot of data more will come. However, we are kind of struggling to some point, because if you calculate how many data we have right now, probably terabyte of audio on your disk. If you try to record HD video, etc., there are plenty more. But it starts to scale in the terms of world of the published audio. And if you calculate how many of take all like 1 billion people, how much of audio they are creating, it's about a couple of zettabytes. And if you scale that to all like 10 billion people that will be in 2050, it will be more around a yottabyte. And in fact, we are in sometimes right now, the whole data, I mean, not all audio, is around 15 zettabyte right now created in the world. Of course, I'm not talking, it's a abstract way of looking at it, but in some way, we want to know what the data is, and the model. Of course, they generalize, but they want to create some. Need to create a lot of nuances. So we need to have picture on that. Anyhow, the limits is the lovely 42, which is also calculated in some physics departments, physics theories. The whole the number stopper is probably 10 to 56, which is a universe. Whole entropy of the universe. Anyhow, there are multiple data, and for that we have a lot of GPUs, also from crypto. But before that, we just discovered GPUs, and there were talks about GPUs here. Of course, you can have one or more, and with more, you can create models like GPT or other related to audio, like Stable AI model or Suno, that just seen a lot of different things and take that into account for general generation or prediction. And if you want to look through the numbers, we are getting crazy amount of scaling, and also the itself the audio, because many the music is being generalized, like demographic growth. People are having microphones everywhere, and they record. It's not it's not about recording studios sometimes anymore, but you have TikToks. You have, of course, the music is not well prepared. It's not a studio like music, but it is. So you want to have and you can record next to the river, and then you can have a speech enhancement, audio enhancement, and also vocal enhancements and models to somehow extract the best out of it, and just keep that recordings. And in order to have the model enhanced, you need to have the bad quality audio to know what is the distortion, at least some of that. And there are plenty of audio bad recordings out there. We can grab it. And I just wanted to show you the scale it grows and mimics yourself. But anyhow, the implication is that in order to process it, you don't you need to have some large computer to do it. And for that, you don't have one like multi-threading, but and parallelization of the processing. But you need to distribute it throughout the nodes and scale it. And it's kind of not trivial. I mean, there are different classes, different departments related to multi-threads, parallel distributed computing, because there are different algorithms for that. You need to capture some kind of taste, how to mangle the data, what are the splits, what is the architecture, and the way you pass the data because of the memory and networking. So that's really complicated. And however, right now because of the machine learning, there are frameworks to go over that. Some are already known because of large computing of physics, of chemistry, of biology, of weather. Some are new because of machine learning, like pure machine learning. And for me myself, I tried to create a model for audio representation, like fundamental, what's called right now fundamental model, that just seen a lot of data, like streamed a lot of data, not like even save them inside of the disk, but just pass through the data just to know what is the distribution of the just samples, and how in a long context, like how they behave, and if you want that, you need to have a lot of data, and then you need to filter the titles. What are the titles of the open to filter the recordings that are open in terms of like Creative Commons. Take what is there and filter out into classify it and prepare for different like buckets to know whether this is recording of music in the wild, this is some studio, because then the training get better if you know the data before. What is the data a little bit, just to mix them while training. But the training itself of the model is not an easy one if you have such a large collection of data. In fact, all current models are trained the way that I'm talking about, like millions of hours. The biggest I've heard is like 15 millions of hours of audio from Google and from Amazon. And for me myself, I pick around 500,000 of recordings throughout like 2 years, and just to gather them, pass them for filtering, and from that, from the bad ones that I don't want to really look into, I got half of them, and then 89,000 of a good quality noise, music, speech related, and around 100,000 hours of only speech. What you do with it, you pseudo label it. I mean, you take different machine learning model, you just run them, the data through them, just to collect a metadata. What is there? It's not perfect, but then you don't have to manually do it, because it's like it was probably not possible to do it anyway. Like 30,000 hours probably is doable in some number of people. Probably like 10 years of around 5 people, or like couple of hours, when you take a whole city. Anyway, I'm trying with all of those data, we was using our cloud, or nodes in the cloud, most clusters, 100 to 200 nodes, to model the data itself. And in terms of training, you define the architecture, pick some parameters, know what you want, and basically just run multiple times, look what is working, and set up the perfect parameters that you want to train for more days. And if you look through the data, the most important is that you try to. It's a stopper, because amount of data, and you know that you need to pick those, you need to process data. Some of the experiments shows that it's perfect. You need to do it's very good results. So you probably do it once, and then you can reuse it to different tasks, like classification, when you then have little data, and you fine tune the model to this particular task. And so typically, if you take this amount of data, it will be around, just for naive processing, like passing through the data, like quite intensive large node, 32 cores or 64 cores, because of the memory issues through output, which blocks you. It's around 30 days, and that's just passing the data without any touching anything else. And if you want to do more, it just grows. And for example, training on this 200 thousand hours of data, not 500. It takes 190 days to do it. Then you can, of course, multiply the nodes, and have like cluster of 12 with 8 GPUs, and shrinks down to some number of like 3 days or 4 days of intense computing. Of course, it can cost, but eventually you shrink down the time from 190 days to only for 1 week. You have the data, and then you can look through what is there, work out there, and repeat the experiment. But anyhow, the solutions can be multiple. Like you want to scale it, and I've shown you that just like grouping and renting a lot more compute, not buying them even. Right now, we don't need to kind of buy HPC, large, scientific university scale compute. You can just rent it from different providers. And there are those systems that called Slurm for scientific, Kubernetes, Hadoop, Spark, that are mostly used in business cases. But there is also Array. It's a system coming from research of Berkeley University, which is one of the best in terms of distributed and parallelized computing. And is well connected to a PyTorch, which is another framework for machine learning computation. And it's a general purpose kind of distributed computing. So it's kind of it can run cluster also in locally, kind of even one computer. It's really simulation, but then also in the cloud with a very quick, rapid movement. So you can develop your algorithm on laptop, and then if you are done, test it here with multiple like distributed functions on your computer, and then pass it through to the larger cluster and see how it goes, probably, and then debug it on your laptop and pass through. So the perfect thing is that on pure Python you can use multiprocessing function, and also in Ray there is this Ray utility multiprocessing, which is the same, but it's kind of better. And if you are not using, you should probably. There is also joblib, and you can mitigate a similar within the Ray itself. It is just a passing of a message passing algorithm and pulling of the workers that do the work itself. But the Ray is kind of three typical systems. One is the Ray core, which is a C++ library that do the basic worker scheduling, etc. And there are those libraries like for data processing, training, tuning, serving, and reinforcement learning. I will not talk on many things, but about these libraries. But in general, there is like this core, and there are like tasks, actors, and objects. And they are interconnected with various systems and libraries, so it's easy to kind of play around, to visualize, train. It's there, very usable, and it's for like around 10 years or 12 years right now being developed. It's open source, but there is a company that governs that, but they earn their money through renting the compute. The company is called Anyscale. But there is a large community that also play with the Ray itself. So as I told you, you can play on your laptop or on a virtual machine, or you can scale it to work it on Kubernetes. It can be within Kubernetes or outside. So it can be as well. I primarily use Ray without Kubernetes because it's similar to Kubernetes, and you just skip the Kubernetes. But some companies have large Kubernetes scale. And for clustering and for nodes, there is this arraylet. There are drivers that governs the machine. There are worker processes, and there is a scheduler that run. But the most important that the whole system is asynchronous and self-rebuilding. So if the head node is gone, all workers are working until the head node. They try to compute the things. If the head node is up, then it will they will resync things and end the job itself. So I told you the most important here is Raylet and some global control store, which is asynchronous, and it shares the data, but it's not. It's a very delicate detail. I will not mention it. So all those are kind of interchangeable, and know which authors are being created and recovered and destroyed. But the node itself is governing. There is no like master who governs everything. The primary component is Raylet. It's made in C++. It's for task scheduling, object management, passing and storing. Most often, there is zero message data passing until so it's lazy data processing. And there are worker process, so you can write your code not only in Python but also in Java and C++ itself. So it's very good library also for for computing distributed. You can just use Ray core to do it. And primary, they just share some pointers to a data space. As you use S3, or it's even faster, but also if you are trying to create a network drive, it will also pass some kind of pointers to the inside of the to the space itself. So it will not pass the data itself. The worker will just grab the data. The lifetime is governed by executing the task. Task is one of the things. Objects actors are objects, classes, let's call them, that just have multiple functions and can store a little bit of data. The actors can play with each other, so they can pass the information through one to another. and the work is done by calling like dot remote, and also for tasks it's also dot remote. It just triggers that. In terms of like prioritization, we can have like pure batch and passing of data like one by one, or some graphs that you define. And in terms of the course and abstractions of those, as I told you, there is a task that are just functions that are stateless. They depend on input output. Actors are more message passing, kind of abstract. They can receive, they can store some state. And there are other like multi-processing pool of workers and some other prioritization. Objects definitely store only the data itself, and those are based on the research that I told you that it even started in 1973. And for actors, here's an example of the code. So you can read the file remotely, then grab that, return that, and it will be there in a cluster. You can pass that data to another function, and it will govern itself how to pass it. Basically, it will communicate. The nodes will communicate with each other depending on which node is computing that, and pass this information through the data store, RPC calls. Anyhow, you can see an example of classes and the task actors. So the primary thing, the call, the trigger is remote, and you just define similar to it's just this decorator, at ray dot remote, or that's at ray that shows that this particular object is within the ray object. So and if you run that within the ray cluster or with a framework, it will just read the itself the code and run it in this ray environment. The API is here, so I've shown you. It just passes the. It's just a cyclic graph of the data, and for host, it remotely shares the local state, but it's primarily you can even force the actor to be on one primary node. You can force to have a number of GPUs. You can have multiple actors on one GPU. So we can have, for example, one GPU and set it up that we have five. I just. Oh yeah, five different models that with a graph one by one, it will govern yourself. There is something called workflow, so we can collect the data processing part with a number of functions, and it can bring together and be optimized for processing. I will not go to details. You can read it later on, and also in the documentation. Especially for RAID data, it uses this very parallelization memory organization called Apache Arrow, and and files that saves that representation into, it's called Parquet, and it's very column wise most often, but it's really efficient in terms of processing. You should look into it. Of course, there are already some number of functions to read standard CSVs, Parquet files, also audio files in terms of wave, but also some organisms like Pandas, NumPy, memory management. You can group them in the map, batch, filter, and some aggregation states in order to, for example, read a file, grab a batch, then filter out and group the data in some way by a column, and they, for example, calculate a mean. And all of that is kind of lazy loading, and it's being governed by scheduler, so it maximizes the through outputs of the whole network. And also, if you use a GPU, it will organize and process and put the data, the exact amount of data. Of course, it's not as optimal as your own kind of kernels and code. But yeah, it's plenty of optimization then, and work almost like I've seen 80 or even 98%, depending of course on processing and functions to use. For data sets, there are some number of way to shuffle the data streaming wise, to load them, to group them while you do the training. There are, of course, functions to use really easily to scale the training. So you basically import rate torch trainer, which will be a optimized version of layout of the actor that within knows what is the PyTorch torch trainer, and you can then run it, and it will be scaled according to your parameters, to number of workers, the GPUs. And there is RayServe to do the inference, to call that, to set up the APIs. You can connect the models in multiple ways, in chains, ensemble trees. You can even connect them dynamically, so switching on depending on the conditions. Ray surface just as previously, it's and as like fast API and other. You just write add serve decorator on the class, and goes as it is. It's an actor, in fact, just governs the model, the execution of the model. And the basic, I need to finish up. So I hope you grasp the knowledge how to deal with this large complexity of ML in data sets. And I've shown you kind of like the framework to couple of those tasks and challenges. And yeah, then everything just processes and grows and works, and you have the model. But always remember to take care of your data, because they just grow. Thank you.